Hello, everyone. Good afternoon. Welcome to the ARC 304. Today in this session, we will talk about reactive systems and how to implement them on AWS. We are going to discuss here how you can make your applications more flexible, scalable, and fault-tolerant so that you can address the new industry requirements that changed so drastically in the past few years. We are going to see the journey from Bitpanda Pro as a concrete example who built a system from ground up, a reactive system from ground up that's able to handle 1.6 million events on peak time while staying cost efficient. My name is Rafael Ramos. I'm a principal solutions architect on AWS, part of the developer acceleration team.
Thanks, Rafa. So, hey, welcome to Summit, everybody. We're getting close to the end of the day, I know, but I think we have an exciting talk for you here. So my name is Chase Abenschein. I'm a senior account manager with AWS in Austria, and I support our startups and scale-ups that are built natively on the AWS cloud and go on to have massive impact both for their customers, their industry segment, and the world, just like Bitpanda Pro that you'll see today. So to make sure you're in the right spot, the agenda will start off looking at the landscape today, why reactive systems are more important than ever, typical use cases that we see with reactive architecture. Then we'll bring back Raphael to define deeper the manifesto around reactive systems. And then what you've been waiting for, we'll bring up Uri from Bitpanda Pro, and they'll discuss their journey and the various architectures they used to scale up in a 24/7 trading environment, uptime environment. And then at the end, we'll recap with some resources for you guys. For example, GitHub repository with CloudFormation templates, so you can build out your own reactive architectures and get started on AWS. OK. So we all know this to be true. Software moves faster and faster and faster. As consumers of software, you know that everyone expects 100% uptime, regardless of how popular an application is. So you'll see this with Bitpanda Pro here today as well. Many of these use cases require millisecond response times. The data sets can grow to petabyte size. And alongside of that, developers are building systems with hundreds of software components, all communicating together, rising for the need for very resilient and reactive architectures. It's crucial. So a couple typical use cases that you see out there. I think what all these have in common that's interesting is they have the potential for millions of events to flow into the backend systems. That means the backend system needs to be able to scale on demand while being fully resilient. So you see this in the manufacturing space. If you have IoT devices spread across machines and factory components, all these connected devices produce lots of data points that need to be analyzed, ingested, aggregated, and then sometimes pushed back out to the devices themselves. The system needs to be responsive. Also, for example, in e-commerce, if you have a product that goes viral on social media, or you have a really successful marketing campaign, there can be a lot of dollars invested on the line. Potentially, you have seasonality in your business, like around a Black Friday event, something like this. You need a system that can handle a lot of visits to your application, a lot of visits to your website, and remain resilient within that demand. And then lastly, again, you'll see within the fintech use case, or crypto in this case, you have 24/7 uptime with tradings globally. And a tweet can change trading volumes in a second. So you need to have, again, a very resilient, reliable response time with your architecture. So with that, let's give Rafa a big hand. Get him excited to come up. And we'll look more and define reactive systems. Thanks.
All right, thanks, Chase. Now, let's start here with a more fundamental question. What are actually reactive systems? Some of you may already be familiar with this concept. That's not something quite new, right? But let's take a closer look into some principles before jumping into the practical examples with Uri and Bitpanda. This here is the architecture of a typical NTR application. You should all be used to this kind of architecture at this point. On the left-hand side, you have the client applications that can run on a web browser or on mobile and so on. And those applications are sending requests to a server and waiting for a response. The server can potentially interact with other components of your ecosystem, like other backend systems, for instance, that would then interact with even more components, like storage systems, databases, and etc. All this communication here happens synchronously, which means that the user, after performing an operation on the client, is waiting for a response. It's blocked waiting for a response. And this approach here can potentially bring even other challenges, like underutilization of server resources that are idle there, which can then impact your costs. And it can bring also tighter coupling between components that can affect your maintainability. This kind of architecture worked for quite some time, and depending on your use case, depending on your application, it can still be valid. But for many industries, as Chase mentioned, requirements changed. Users do expect 100% uptime, and they, depending on the industry, depending on the use case, they require sub-second or even lower response time. So to address this issue, back in 2014, the Reactive Manifesto was released. And the manifesto is basically a collection of principles that define the characteristics of a reactive system. And in a nutshell, reactive systems must be responsive, meaning that they must respond to user requests in a timely manner. They must also do that, be responsive, even when facing a failure, meaning that the system must be resilient. And they must also be elastic, scaling dynamically by adding or removing resources whenever needed. And lastly, reactive systems must be message-driven, meaning that the components in the system should communicate with each other asynchronously using message passing. So let's talk about some strategies to implement each of those concepts that you can apply in your own organization, in your own system. First one, responsive. So the key word here is latency. To increase the responsiveness of your application, you have to pay special attention to latency. And for that, consider using, for instance, a load balancer as the entry point for your client applications, because the load balancer can then distribute the traffic across multiple targets, depending, for instance, on their availability or depending on their health status at that point in time. Second, use caching. It can be in-memory caching inside the application. It can be external caches like Redis or Memcached. About elasticity, according to the AWS well-architected framework, elasticity means the ability to acquire resources when you need them and release those resources when they are no longer needed. And in the cloud, you want to take full benefit of that and make it automatically. Some services, if you're using AWS, hope you are, like AWS Lambda, they already have this kind of elastic scalability built in. But when that's not the case, when you're using a different subset of services, aim to apply horizontal scaling wherever possible. So instead of having one or very few machines, large machines, to handle all the workload, you should aim to have multiple smaller compute resources that you can allocate, that you can spin off on demand. The third principle is the ability for the system to recover a failure. And actually, you should design your system taking for granted that your system at some point is going to fail. And the failure here, I mean anything from an attack to an abnormal traffic spike, for instance. So for that, an important strategy is to apply replication and redundancy whenever possible, because you don't want to be relying on a single instance of your components. And on top of that, you should try to isolate one component from another in a way that if one component fails, your whole system is still able to work, even if you have to provide a limited number of features or limited capacity to your customers. So we talked so far about decoupled and isolated components, right? And the last principle is related to how those components communicate with each other. In essence, what we want here is to avoid that one component is blocked waiting for another to perform an operation. To mitigate that, aim to use asynchronous communication with push instead of pull. For example, you can use a publish-subscribe model here so that downstream components in your architecture are notified automatically and asynchronously when something happens in the system so that it can take some action. Another example that you can apply is event sourcing in conjunction with CQRS so that you can decouple read from write workloads to optimize even further. Now, let's see those principles in practice with a real-world application implemented on AWS by Bitpanda Pro. You right?
Thank you, Rafa. Thank you for the introduction. OK, so we heard about reactive systems, some theory, and I will attempt to provide a more practical view. So I'm Yorai Zachar, head of engineering at Bitpanda Pro. Bitpanda Pro is centralized crypto exchange that we established in Austria back in 2019 by parent company Bitpanda Brokerage. We started this project as a very, very small team of 4 Java engineers, and a grand vision to apply principles of reactive programming to launching a trading platform that would rival some of the bigger US competitors. We had to take a very pragmatic engineering strategy due to our size. We also didn't have ideal time to market. And that strategy was to leverage fully managed cloud services, services that would scale with our business. OK, so I might have mentioned there are quite a few crypto exchanges out there. It's not much known about this business idea. And each of our competitors is vying for customer attention. So what did we wanted to achieve to differentiate ourselves from the competition was by erecting these 5 key tenets in our mission statement. Number 1, we need to guarantee execution of clients' orders in a reliable, safe manner. We want to offer best market prices. How do we achieve this? With very deep crypto liquidity pool. Number 2, very important, I hope you agree with me, is to establish customer trust. And we want to do this by being fully regulated and based in the EU. Number 3, state-of-the-art, low latency and high throughput order execution is how we want to achieve this. Number 4, really, really important to us is to provide seamless, secure funds management. And of course, with that comes speedy withdrawal processing. And finally, number 5, how do we present ourselves to the world? Through intuitive UI. And with that comes high customer satisfaction when they use our mobile apps. At Bitpanda Pro, we're constantly obsessing about the speed of our code. Since 2019, we've seen the crypto industry experiencing a strong push towards high-frequency trading. And as such, our target 99th percentile of order execution should be no worse than 1 millisecond. This we want to do while we sustain a load of 50,000 orders per second. Just want to sink that in. That is 50,000 times accurate locking, unlocking of clients' account balances, matching of the order with counterparty, settling of the trade. Of course, with great speed comes the risk of lax security and compliance oversight. This is our second challenge. Regardless of how many orders we are churning, every single financial transaction is subject to strict regulatory governance, such as know your customer, know your business, know your transaction, full customer due diligence. Of course, we are a startup, so whatever we do should stay within startup budget. The foundations we built, put in place, they really need to prove themselves to be worthy of powering a business growth of at least 10x. So we've seen this slide. We'll not go into too many details. So I just want to kind of like have a quick refresher. How did we apply these principles in practice? How did we achieve message-driven, loosely coupled deployment, highly elastic at times of rapid client activity spikes? How did we achieve robustness to faults? And ultimately, very responsive trading experience to our customers. Just a small disclaimer. It's not easy. It's taking us more than 1 attempt to get this right. We're actually still very hard at work optimizing our setup in AWS to deliver on all these key business objectives, especially with the advent of HFT, high-frequency trading in the crypto trading industry. The level of complexity associated with reducing latency further, increasing throughput, the complexity exponentially rises. So when we began, our first reasoning about what we wanted to do in AWS breaks down as follows. We're 4 Java engineers who are fairly new to AWS services. We want to focus on what we do well, and that is writing code that powers our trading platform. Therefore, we perceived Kubernetes back in 2018 as a fairly risky and complex endeavor, especially for a team that lacked the necessary platform engineering expertise. Therefore, a decision was made to go for ECS Fargate. ECS Fargate had a lot of complexity in sizing the underlying container cluster, allowed us to build CI/CD pipelines with great ease. Number 2, microservices. So microservices back in 2019, that was a thing. There was a lot of hype that was peaking, and we actually took a slightly more conservative wait-and-see approach and decided to opt for a monolithic deployment with ECS Fargate as backing tasks. In the application layer, that was a no-brainer. We bet on a reactive, unopinionated Java framework called Vertex. Vertex is one of the fastest reactive frameworks out there, available to developers who must meet strict non-functional requirements. In contrast to the mainstream frameworks, such as Spring Boot, it comes with far fewer dependencies, promotes non-blocking asynchronous execution, and leads developers to write code where strongly isolated thread contexts communicate by message passing. Next, we wanted to solve the problem of balancing our responsiveness against unnecessary over-provisioning of the service. Of course, over-provisioning is not good. That drives up your cost in AWS. We followed the well-established approach of putting an elastic application load balancer in front of the ECS Fargate deployment. There was also auto-scaling group involved. That was based on request rate metric. Now, Java workloads implemented with Vertex are non-blocking and non-CPU bound. Every deployed JVM is high concurrency, high throughput HTTP server. We made extra effort in establishing maximum number of requests per second that we can easily achieve before the service degrades. And we did this by conducting loads and loads of load tests. Once we entered production environment, we let the load balancer and ASGs do the rest of the work. Following through with ECS Fargate, we then deployed our services across 3 availability zones and had the ease of mind that service degradation in one zone will not dramatically create a cascading failure or impact our quality of service. The last piece of the puzzle we had to solve was deciding on relational ACID compliant database. The nature of our business does not allow for any non-deterministic order execution, especially when we're handling clients' funds, and therefore we need strong transactional guarantees when we're modifying financial records. Since we lack the necessary DBA expertise to operate custom PostgreSQL fleet, we opted for Aurora RDS. Now, putting it all together, our very first deployment in AWS looks something like this. We used one AWS account, and where we had an edge service deployment. We managed this in Terraform. We had a Flyway project to perform database migrations in Aurora. This is probably one of the simplest deployment models with a traditional relational database, Java-based edge service that allows for quick bootstrap of the production environment, and you can really follow the dream of infrastructure as code. OK, so very early on, we realized that simplicity of the monolithic deployment comes with some serious problems. For one bundling of our matching engine with all offered traded pairs, roll out horizontal scaling. EC Supervisor only offers rudimentary controls over how many desired tasks should be provisioned at any given time. Electing a single leader just isn't possible. So no clustering. Second, as we continuously develop the product and work on new features, we quickly realized that bundling of independent, separable domains results in a large redeployment overhead. We quickly hit some resource constraints of a single ECS Fargate instance. Lastly, while the horizontal scaling of Aurora allowed us to grow the product capacity, we learned that optimizing PostgreSQL database for both writes and reads is a very complex exercise. Suffices to say, monolithic deployment was a clear dead end. So to address these problems, in our second take, we tentatively embraced the microservices hype and jumped on the Apache Kafka bandwagon. And the game plan looked a little bit like this. Mind you, this is 2018, or 3 years prior AWS MSK's GA. Apache Kafka just stabilized its first major release. By evicting Trade Engine out of the monolith, however, we achieved 2 important milestones. Number 1, we can now have a natural back pressure control, and that for every provision market. Number 2, by carving out a single topic partition for every traded pair, we can naturally scale the system up and down. Over the years of operating our crypto exchange, we learned that delisting of traded instruments actually occurs more frequently than in traditional financial systems with stable assets. We really liked how a Kafka-based message passing system unlocked this level of elasticity. It was about the same time when we embraced message passing and split up the monolith that we discovered the next key AWS service, DynamoDB. It doesn't really require any introduction. Raphael mentioned CQRS at the beginning. Well, this is what it looks like in practice. We use Kafka message passing in DynamoDB heavily to outsource all of our API reads. That is, reading client orders, reading client trades, checking account balance. That in turn allowed us to focus on optimizing PostgreSQL for a write-heavy workload. DynamoDB offered just a sweet spot of materializing all after-the-fact trading events with a single-digit latency. As the clients ramped up trading activity, we could comfortably scale out horizontally with ECS Fargate. Each additional provision task would begin consumption from assigned Kafka topic partition. This allowed us to soak up abrupt load increases. And again, so the second take, second iteration, AWS breaks down as edge services deployed across 3 availability zones. We've got our asset persistence. We've got our message passing. Trading engines, completely outsourced, split out from the monolith. And finally, a bunch of DynamoDB tables holding historical data. So far, a lot of theory about reactive systems, and I really need to address the elephant in the room, how the system actually performed. So this picture, this is a picture of CloudWatch metrics, which pretty much captures what crypto markets look like, what our system looked like roughly a year ago. There was a period of relative calm. During quiet hours, we would push about 3,000 transactions. Intraday hours, client activity would peak to 8,000 trade events per minute. OK, towards the end of Q1 2022, things got really interesting. crypto markets underwent a period of increased volatility. Trading platform would suddenly go from low period of trading activity to an abrupt trading frenzy. Traders attempting to regain foothold in the global market sell-off. It was during this period when reactive systems experienced a scale-up, and mind you, this is during business hours, scale-up of 10x or greater. This screenshot captures an all-time high of 1.6 million trade events. We processed in May 11, 2022, 1 o'clock UTC. Plus, I'm offering a breakdown of the process events. In CloudWatch Metrics, we monitor not just the happy path, but also we're always on the lookout for errors. So we have in red, failed system errors. We've got unprocessable application level errors. And then we've got duplicated events. Duplicated events can signal degraded system state. We are very pleased to see the system pass this period of market volatility with exactly 0 errors. Lessons learned. I want to begin with the goods. This stack just works. We know it because our site reliability engineers told us so. It's battle tested, and it follows key reactive systems principles. Now for the bad. We can actually go only as fast as our relational database allows. Don't get me wrong, Aurora PostgreSQL is no slouch, but one really needs to purchase a large enough instance to comfortably soak up spikes in user activity. This, in turn, drives up cost. With DynamoDB, this is a different story. System scales transparently with the loads increase and pretty much indefinitely. Well, or as long as the AWS budget goes. However, retaining 10 years of trading activity, and here I mean every single submitted order, match trade, this is a lot of data, amounts to tens of terabytes. Migrating this data, because we developed a new feature, because we changed API, that can be super expensive. There has actually ever been just one instance when we attempted to migrate this data. And out of curiosity, it took us 2 weeks of constant execution time to get the job done. Worse still, we're failing on our key performance target. That is end-to-end latency. The system we built comprises many moving parts, some of which equals the time required to respond to client with authoritative answer on what happened to the submitted order. We spent a significant amount of time optimizing performance of Aurora cluster, Kafka cluster, only to achieve P99 of 100 milliseconds. That is for a round trip time. That is still 100 times worse than our performance target of sub-millisecond order execution. So what are we going to do about it? Well, just like any other sensible group of engineers, we're going to throw all of our accomplishments out of the window, start again. This time we're approaching this problem differently by embracing a more minimalistic approach. We want to remove the number of moving parts from the order execution hot path. To be more precise, we're going to keep it just to one, and that's going to be a compute-optimized EC2 instance. Through our quest of performance optimizations, we came across Chronicle Software. And they specialize in developing ultra-low latency trading technology. It's compatible with Vertex, and it's otherwise unopinionated. If you haven't heard of them, highly recommend to check them out. And just to clarify on that note, what I meant by expanding our AWS universe, this diagram paints a slightly more detailed picture of what our operation in AWS looks like today. Trade engine, integration workloads are still there in their respective workload accounts. VPCs demarcate clear domain boundaries. with other subsystems. Collectively, we deliver all product capabilities to our customers using all these accounts. Suffice it to say, we've come a long way since the single ECS Fargate monolith deployment. And we're not really planning on abandoning our big guns, Kafka, DynamoDB, or RDS. However, since we are now elevating speed of order execution, our key product capability, we have much better understanding of the established upper bound on data latency. Kafka continues to play a crucial role in providing unparalleled throughput when distributing data to historical data tier. Equally, workloads which require strict transactional guarantees continue utilizing Aurora. And for those, we've built ETL pipelines which ship data directly to our warehouse for analytics. It is with this approach we can keep operational planes small, leverage much cheaper and scalable S3 for long-term data retention. In my concluding remarks, allow me to share our view on building reactive systems on AWS. First, we categorize our runtime environments into ephemeral, highly sensitive workloads that execute as AWS Lambda functions. As an example, processing clients' withdrawal requests is a well-defined function with input and output. We limit execution time and loading of sensitive secrets to just the time needed to process the client's request. Next, and in stark contrast to Lambdas, we have high-performing trade engine deployed on EC2. This workload never shuts down. Any suboptimal performance has a direct impact on our business. Finally, there is super elastic scale-out workloads, battle-tested ECS Fargate. Among other things, it works really, really well as HTTP Vertex server, near real-time data transformation workloads that is coupled to Kafka. As for message passing, we learned to orchestrate customer request processing by daisy chaining events that span multiple AWS accounts using AWS EventBridge. EventBridge is often coupled directly to API Gateway, which allows us to implement our authorization layer, acts as an internal proxy, and point of service for third-party webhooks. Finally, and this probably doesn't come as a surprise, we learned to lean on SQS for delivering at least once messaging guarantee. Our business continuity is woven into different types of storage systems. They are classified by a metric that we call decaying time value of data. In other words, the utility of data decays over time, and it becomes less and less interesting to the customer and the business. As this happens, the utility of different data classes decreases at a different pace. For example, customer is a magnitude less interested in a specific canceled, unfilled order from 3 months ago than the current market price of Bitcoin. As such, it is really this combination of a wide spectrum of storage solutions coupled to specialized runtime environments, which are loosely coupled, event-driven, and really bring about the nature of reactive systems at Bitpanda Pro on AWS. Thank you for your attention.
All righty. So one more round of applause for you, right? That was nice, huh? Okie dokie. So just to give you guys kind of a recap, we'll get into some resources as well. So get your phones out. You'll want to take a picture for some of these links. So today we heard about a startup, small team, under huge growth pressures, huge cost pressures. They're regulated. They're up 100% of the time. They're able to scale their applications to millions of events and iterate on behalf of their customers all while pushing now pushing the boundaries of latency reduction. So within that journey, there's four key themes that are echoed. And these are the four biggest reasons that customers choose to build their reactive architectures on AWS. So agility, elasticity, these are built into the services that are underpinning a reactive architecture. You can very quickly develop and roll out new applications. You can deploy these services in minutes, and they're capable of scaling massively on demand and resiliently. So using serverless features, we heard ECS Fargate, Amazon Aurora Serverless, Event Bridge, API Gateway. Bitpanda Pro was able to reduce overhead in terms of the time they spent provisioning their architecture and reacting to events, with the double effect of saving costs while increasing their time to innovate on behalf of customers. So now it's your turn to get started. So first stop, if you haven't set up your Skill Builder account yet, I highly encourage you to. Join the millions of AWS users that are using AWS training and certification. There's 600 free digital courses. There's also the Skill Builder subscription. This provides companies access to administrative controls and premium content as well. And then here's where you'll want to take some pictures. So first, you'll find the GitHub repository that has a CloudFormation template that'll allow you to set up your own reactive microservices architecture. So a few services that you may have not heard today that are in there would be Kinesis Streams, Elasticache is in there, but also the ones Uri mentioned they use as well, Fargate, Lambda, the Elastic Container Service as well. The second two, a blog post and a white paper if you want to get deeper into the principles, the design principles, best practices behind these, and then the Vertex project that Uri mentions is there as well. So thank you guys very much. We'll be sticking around on stage for a few more minutes so for a Q&A. So if you guys have more questions for Uri, please come on up and we'll get the mics off and answer questions. So thank you so much.